I hope. So.
Full screen. Yeah, very good.
Does it work?
Yes, yes, it's wonderful. All right, so please, Alexander Bobenko from Technical University in Berlin. The title of the talk is The Bonnet Problem. Is a surface characterized by its metric and curvatures? Please.
Okay, thank you very much. It's a pleasure to give a talk here. I apologize for my voice. I got cold, yeah, so but I hope it will be understandable. So I will talk about our recent result with Tim Hoffman and Andy Zageman-Furnas. And it's a result in classical differential geometry. So we are considering classical surfaces in classical three-dimensional space and discuss their properties. And why it's related to what we have in this conference is because there are many steps in the solution of this problem. And some of them, they use discretizations of geometric surfaces. And these are so-called structure-preserving discretizations. And they can be quite useful in more general setup. So let me start just with explanation of the problem. And first two pages, they're just pages from standard class in differential geometry 1. So if you consider, as I said, surfaces in three-dimensional space, parametrized surfaces, then the standard way to describe them is to consider the immersion function and to consider the Gauss map, the normal map to the surface. You see them both in these pictures. And as soon as you have them, you define the first and the second fundamental forms. They are presented here. The first fundamental form is just the metric on your surface. And the second fundamental form deals with Gauss map. Yeah. So, and then these data, the first and the fundamental and the second fundamental form, they are not independent. So their coefficients should satisfy some partial nonlinear differential equations. They are called Gauss-Kadazza equation. And provided these Gauss-Kadazza equations are satisfied, you have a surface. So given two fundamental forms, or the metric and the second fundamental form, that satisfy these Gauss-Kadazza equations, then they locally determine an immersion, and this immersion is unique up to rigid motion. That's classical differential geometry. This is so-called Bonnet theorem, how one can get surface from its fundamental form. So again, what do we have here? We have here over-prescribed data that are not independent, that should satisfy some compatibility conditions. And these compatibility conditions are really quite involved. And therefore, a natural question would be whether some reduced data are possible, whether it's really necessary to use both fundamental forms. And this question about reduced data can be treated as usually in differential geometry locally, globally, and also the questions are existence question and uniqueness question, quite classical topic in differential geometry. So maybe I will start with some mentioning a famous problem in this setup. So it's so-called isometric embedding problem. Quite natural thing to start with is metric. And the question is the surface in R3 with a given metric? So you give metric and then whether it determines your surface. So this means whether your intrinsic geometry determines the extrinsic geometry. And there are plenty of classical results about this, starting with Darboux. That was local classification, so-called Darboux equation, which is even locally still unsolved in the general setup. Globally, one can mention here proof by, well, the problem by Weil on sphere with convex metric, and the quite fundamental result of Alexandrov, Nirenberg, Pogorelov, existence regularity, or the result by Hilbert that there are no immersed hyperbolic planes. So if you have the whole hyperbolic plane, then it can't be immersed in R3. And also higher dimensions, famous results by Nash, or uniqueness. Here one can mention a result by Confossen that closed convex surfaces are rigid, and in general there may exist some isometric deformations. So that's a quite fundamental problem, isometric embedding problem, and we see that metric is not enough. Isometric deformations are possible. So let me now explain you the problem we are investigating. It is so-called the Bonnet problem. The next step would be, what can we tell about our surface if we know metric and curvatures? So do metrics and curvatures determine a surface? Surface has two principal curvatures at every point, or equivalently, it has Gaussian curvature and mean curvature, which are symmetric functions of these principal curvatures. And there is famous theorem by Gauss, which tells that metric determines the Gaussian curvature. So this means that the question is really whether a metric and mean curvature determine a unique immersion. And this problem was, of course, quite well investigated, and it was first classically investigated locally. So what was known about local problem? So we have metric, we have mean curvature, whether they determine a surface uniquely. Generically, this is the case. Metric and mean curvature locally determine a unique surface, a unique immersion. And three exceptions from this uniqueness were known already to Bonnet. So these are, let me mention you these three cases. The first case is the case of constant mean curvature surfaces. So you have one parameter family, and I show you just this demonstration how a helicoid deforms to a catenoid. And that's one parameter family of isometric deformations that, and we stay within the class of minimal surfaces. This is definitely an example of non-uniqueness. The second case is the case so-called Bonnet families, when you have non-constant mean curvature surface and you have still one parameter family of deformations. So there is a local theory also developed by Cartan, Chern, and other people. And it turns out that this theory is quite interesting, and it is related to Penlevé equations. So these are two classical cases. But for us, it will be interesting case of Bonnet pairs, when you have exactly two surfaces with non-constant mean curvature. So locally, the problem has been solved. It's clear what is going on. And the question is, what happens globally? What does it mean globally? Globally means that you're considering closed surfaces, surfaces without boundary. And then it's a classical result of 1980 by Tribuzzi, that if you consider a genus zero surface, you consider topological surfaces with the metric and non-constant mean curvature, and they determine at most one immersion. So here you have uniqueness. There are no two surfaces. If you look at surfaces of genus greater than 0, starting with tori, then it's also known that at most two immersions are possible. And now let me formulate a global Bonnet problem. We will investigate, do there exist two compact immersions that are related by mean curvature preserving isometry? You have two surfaces, they are both compact. You have a map of one surface to other surface. It's an isometry, and this isometry preserves the mean curvature function. One should mention here that high genus constant mean curvature surfaces exist. So here you see an example, but it's not known whether you can find an isometric surface which is also closed. It's known that surfaces of a Bonnet family are not compact. So, and therefore, the only way to the only gap which is remaining now is the question, do there exist compact Bonnet pairs? And there were some partial results about this. So it was not clear whether they really exist or not exist. There were papers aiming at proving of both things, but mostly about finding conditions for non-existence. So it was maybe a common belief or partial belief that such surfaces do not exist. So, and now let me formulate you, show the main result we've obtained, again with Tim Hoffman and Andy Zagerman for us. There exist two non-congruent immersed tori, F plus and M minus, that correspond to the mean curvature preserving isometries. So you see two such tori in this picture. You see that the surfaces do have self-intersections. They're rather complicated, but they're smooth surfaces without singularities. And surface F minus is isometric to surface F plus. There is a map, the isometry of one surface to another. Here you see two generators on this tori, the blue one and the orange one. So the claim is that also it's in an intrinsic isometry, the surfaces are non-congruent. Of course, if you take a compact surface, rotate it in R3, you get another example which is isometric, but it's the same surface. So here the surfaces are non-congruent, and you can see this in the these images. The bubbles in the second image here are further, so they're a little bit far apart. And two orange lines here, they are isometric. They do correspond. The mean curvatures along these lines are the same, but they are not congruent. It's rather easy to see. Okay, so that's the main result. And maybe I will show you which parts of the surfaces correspond. So here they are marked in appropriate colors. And that's the plan of my talk. Yeah. So maybe I will not be able to explain you all the details, but I try to explain to you what kind of technique we are using, what kind of ideas, and then especially how this discrete local theory of Bonnet pairs comes into game. Okay, first we start from the very beginning, and now I am talking about special class of surfaces. So these are called so-called isothermic surfaces. They are special surfaces. You can parameterize any surface in R3 conformally. You can parameterize any surface in R3 by its curvature lines. But if you can parameterize a surface conformally by its curvature lines, it's an isothermic surface. It's a special class of surfaces. So geometrically, you can see this as the property that curvature lines form infinitesimal squares. If you have such a surface, so there are many special cases. For example, constant mean curvature surfaces, minimal surfaces, quadrics, and surfaces of revolution, many. Yeah. So, but still, it's special class of special surfaces. So, if you have a surface, then you have so-called an isothermic surface. Then you have a so-called dual surface, and that's very important for us in the future. So. You have a metric, e to the 2h is a conformal factor of your metric, and the immersion f, that's your surface. But then you do the following thing. You define a one form, u and v are these parameters on your surface, this coordinate representation of this surface, and build the following thing. You change the sign at the second derivative of the second tangent vector and divide by the conformal factor. So for it turns out that this is a closed one form. So it determines as a surface, and moreover, this is an isothermic surface, and this is a dual transformation. If you apply it again, you're back. So the surface and its isothermic and its dual surface, they have parallel tangent planes, obviously. So now I explain the relation of isothermic surfaces to Bonnet pairs. This is a result by Kamberov-Pedit-Pinkall, which is well, non-classical, and it uses quaternionic surface theory. In this case, one should be able to multiply surfaces, and to do this, you describe surfaces as imaginary quaternions. You identify the three-dimensional space with the space of imaginary quaternions. Then the rotation in this space is just the adjoint action of the quaternion group, and you have an analog of complex conjugation. That's a conjugation of quaternions. So again, q bar, so then your surface represented as a quaternion times q is a conformal transformation. It's a rotation and a scaling. And every surface can be, of course, parametrized this way, since represented this way, because R3 is identified with imaginary quaternions, and then three imaginary quaternions, I, J, and K, are built just a basis in R3. If you want, you can think about SU2 Lie algebra, so which is three-dimensional and which is identified with R3. Okay, so now what's the result? What's the relation of isothermic surfaces and Bonnet pairs? That's, as I said, the result of Kamberov-Pedit-Pinkall. And it says that two immersions, F plus and F minus, now represented as quaternions, form a Bonnet pair if and only if there is an isothermic surface somewhere in between, and real number, such that they both, F plus and F minus, can be obtained from these isothermic surfaces, So let us look at this formula in this gray box. F is our isothermic surface. It's an imaginary quaternion. Epsilon plus F is quaternion. And dF star is the imaginary quaternion, which is one form and which is determined by our dual isothermic surface. We take this dual isothermic surface one form and apply conformal transformation, but this stretch and rotation depend on our original isothermic surface, which is here. So it's quite interesting algebraic formula, and geometrically it's difficult to understand what is going on. Yeah. So, but what is important for us is that if we have an isothermic surface, then we can dualize it, get the dual isothermic surface, and generate two Bonnet immersions. You see, this is the formula on the level of one forms. So if you have a topological disk, then of course you can integrate and it determines your surface. But if you have closed surfaces which may have periods, then of course it's a big question whether the periods are there or not. So, and let me, so this picture to the right demonstrates you the relation between these three surfaces. The surface to the left is the isothermic surface, and two surfaces to the right are F plus and F minus. And again, this is a local theory. We take a small disk or large disk, the simply connected domain, take an isothermic surface, and after that apply this formula, and that's what you see, what is F plus and F minus. Okay, maybe as a side remark is that in this quaternionic language, the formula for the dual isothermic surface simplifies, and you have this derivative Fu and Fv, which are imaginary quaternion inversed, and you integrate them. Okay, so now shortly about periodicity conditions. Just let me explain you what's the problem. So now we are going to use this representation globally and analyze what kind of periodicity conditions appear and how one can generate closed examples with this formula. Well, that's several ways to rewrite this formula, but let us look what do we have in this box. You see, this we are going to integrate this df plus minus because we need a surface, and we are interested in a condition whether the surface has a period and not only its one form. The periodicity conditions are quite involved, and you see here that you have first the condition that your surface F seems to be closed, then some conditions like this for the dual surface, and also some conditions which we still have to understand. Okay. So quite involved periodicity conditions. Not quite clear how to control the periodicity and what to do. So it's known that, well, we will focus on a genus 1 case. We will construct tori. And in this case, it's known that Bonnet surfaces, if they exist, they don't have umbilic points, and this simplifies the theory a little bit. So now the big question is, where do we look for such a compact isothermic surface, even in the genus 1 case? So if we have such a surface, then we can substitute it here, but we should be able to control the periodicity. Okay, and now I make a big jump, and I will jump to discrete local theory of Bonnet pairs. So because it's not quite clear how to treat this problem further in all its generality in the smooth case. So what we are going to do, we are going to consider a similar discrete problem. And that's the place where the discrete differential geometry comes into play. We consider immersions now not of R2, but of Z2, and our surfaces are parametrized surfaces. They have quadrilaterals. It's not, it's a discretization of a parametrized surface, but we are interested in rather special discretization. So they are so-called structure preserving discretizations. And these discrete isothermic surfaces were defined quite time ago. And all this theory is based essentially on the theory of integrable systems, but it can be formulated geometrically without mentioning this integrability. So what is discrete isothermic surface? It's a map of Z2 to R3. So we have quadrilaterals. And about these quadrilaterals, we know first that they are planar. All of them must be planar. The second condition is that they are circular, so that they lie on circles. So there are circumscribed circles for all these quadrilaterals. And moreover, the cross ratios of 4 points of any quadrilateral is equal to -1. The cross ratio, it's just a standard complex cross ratio of 4 points in the complex plane. And this means that you have so-called conformal squares. These are Möbius images of your standard square. All these conditions can be formulated in one condition, that the quaternionic cross ratio is equal to -1. That's a definition. That's a definition, but it was proven that it's quite useful, that it has a lot of interesting, important properties. And in particular, for such discrete surfaces, dual discrete isothermic surfaces were defined. And the formulas are quite the same as in the smooth case. You just take an edge, which is an imaginary quaternion, and take the inverse quaternion, and it turns out that the one form is closed. So it defines you the dual isothermic surface. And now, what was quite important for us was some recent paper, which I'm not quite sure that it already exists. It's a paper of Hoffman, Zagerman, Furnas, and Wardetsky about the relation of discrete isothermic surfaces with discrete Bonnet pairs. So this is the formula suggested in this paper, which is a quite natural geometric discretization of Kamberov-Pedit-Pinkall formula. And you can see that the formula is almost the same. You have one form, which is now defined on an edge. It's a difference of two vertices. The coordinates of two vertices is just an edge of your isothermic surface. And there is an adjoint, it's not an adjoint action. You multiply it from the left and from the right by a similar discrete isothermic quaternions coming from your discrete isothermic surface. The difference is that now, since you have a final edge, you have two vertices, the left vertex and the right vertex, and therefore from the right and from the left, you use the rotation matrices determined by your isothermic surface at the corresponding vertices. So you see they are different from the left and from the right. Previously, they were the same, and it was just a joint action. And it turns out that if you just postulate this formula, which is quite natural geometric definition, quite natural geometric discretization of the smooth formula, then you do have closed one forms, and you obtain two surfaces. And then one can justify and explain why it can be seen that these two surfaces are isothermic and of constant and of with the same mean curvature. So that's all has been done by in this paper by Hoffman, Zagerman, Furnas, and Wardetsky. So what is our next step? What is the idea? To do computational experiments, well, in classical differential geometry in this discrete setup. We consider a torus which is 5 times 7 points big, and treat the coordinates, the Euclidean coordinates of these points as our free parameters. Then we vary them in such a way that the surface F is an isothermic surface, and it's a torus. And also, these F plus and F minus surfaces are also tori. You see, it's highly non-linear variational problem. And as I said, our parameters are just the coordinates of all these 7 times 5 points. So, and it turns out that if you do these numerical experiments, you obtain something like this, yeah? So what you see here seems to be, looks like a mess, but it is not. It's a discrete isothermic torus such that if you create F plus and F minus using these formulas, they look also quite discrete, but they are tori. All the periodicity conditions are satisfied. And what is important that you should look maybe more carefully on these examples and try to understand what we have obtained. So you see, there are these blue and yellow, orange parameter lines. Yeah, they are curvature lines. And it turns out that on our torus, which we have this in this discrete case, the blue parameter lines, the blue lines that consist of 5 points only, they are all planar. And that's a result of numerical computation of this optimization problem. So they are all planar. And moreover, these orange lines, the second family, is spherical in this case. And again, I'm talking now about this isothermic surface, which is used to generate a Bonnet pair. Now we have learned something from the smooth theory, and we are back to from the discrete theory, and we are back to the smooth theory. So that's the third part of my talk, which is the most technical one. But the idea is now clear. We should consider isothermic surfaces with one family of planar curvature lines. We consider this class and try to generate tori from such isothermic tori with one family of planar curvature lines. And then you just look what is known about this. This problem was investigated by Darboux. Darboux himself has classified all of them. And there are several interesting properties. Essentially, the most important thing is that these planar curvature lines, they can be described explicitly. That's this curve gamma. And you take this curve gamma, they are given by explicit functions. And you can generate the whole surface by properly rotating the corresponding planes and gluing the corresponding lines together. So the final formula for your surface looks like this. F is just this planar curvature line, which I will tell you how to describe it, rotated by quaternions in the v direction, and this rotation depends on v only. So rotate the plane while traversing the family of planar curves. That's the result by Darboux. So this is an isothermic surface you see here, and this is a Bonnet pair which can be obtained from this. So what happens globally? Again, Darboux has considered the problem only locally. And if we want to obtain an isothermic torus, that's the formula for the curves. And then if you look carefully, you see that there are no closed curves, and they were supposed to be our planar curvature lines, and we would like to generate a torus. So that seems to be the end of the story. And after that, one can stop and say, okay, there is no way to generate surfaces this way. But stay motivated. So first, we have seen that such examples exist in the discrete case. And also we know that constant mean curvature tori also exist, and they with planar curvature lines. And this is an example of isothermic surface. So this means that this classification of Darboux was not quite complete. And there is a second real reduction which Darboux hasn't studied. So it deals with elliptic functions, and the elliptic functions are defined on a torus. And if this torus has a real involution, then there are two types: a rectangular type, which is quite classical, and you can see this in every textbook on elliptic functions. But also there is a rhombic type, when your parallelogram of periods is symmetric with respect to the diagonal. And that's the case which Darboux doesn't consider, and that's the case which gives us closed curvature lines. So we obtain a classification of isothermic cylinders with one family of closed planar curvature lines. And then, so there are many technical steps here with reparametrization function. But you see, you take such curves that are given explicitly, and now you rotate them into other direction. And this rotation is described by an ordinary differential equation. But anyway, if you use this differential equation, you get a piece of a surface and get a fundamental piece of your Riemann of your torus. So something like it is shown here. And it's also clear that to be able to obtain a torus from this fundamental piece, you need this angle to be rational. So everything simplifies a lot. That's the most crucial thing. If we have planar curvature lines, these periodicity conditions I have presented you. So maybe I will not go into detail. I simply say that one part of these periodicity conditions is your surface F is a torus, your dual surface is a torus, and if you apply Möbius transformation, take the inverse surface F inverse and dualize it, it also must be a torus. So these are important periodicity conditions, but that's not all. So there is more. And if you would like to not only do numerical experiments, but really prove that these surfaces exist, doing research in differential geometry, then it turns out that both conditions, these periodicity conditions, are analytically intractable, because you have an order in the differential equations and you can't solve it, and but you should somehow control the periodicity. So now we remember that we had in our discrete case the second family of spherical curvature lines, and we will try to obtain an isothermic torus with planar and spherical curvature lines, the second family of spherical. And the claim is that there exists an isothermic torus with planar and spherical curvature lines that give rise to compact Bonnet pairs. I maybe will be short about this and just show you images. So these are images of compact Bonnet pairs from isothermic torus with planar and spherical curvature lines. F is an isothermic torus, fundamental piece. F plus and F minus are the pieces of the corresponding Bonnet pair. You see that the corresponding curves are non-congruent. So they are shown here in this image to the right. They have different distances between the endpoints. So, and then you simply generate surfaces from this fundamental piece, and these are the corresponding images. There are many. They are parameterized by these rotation angles with 3-fold symmetry, with 4-fold symmetry. It turns out that it's just one surface, yeah, and we wanted to have both. It's a strange thing. We have F plus and F minus, and they are related by reflection isometry, but the mean curvature preserving isometry is not intrinsic. So the last step is to prove that you can perturb away from spherical curvature lines, preserving all these periodicity properties. You can do this in a mathematically precise way and generate two different surfaces that are isometric and that are related and so that this isometry preserves the mean curvature. So then this is a main example, compact Bonnet pairs with 2-fold rotational symmetry. And so what we have learned, that's our main result, our main theorem. And one more thing is that the construction retains a functional freedom. There are many such surfaces. These are maybe one of the simplest, but it's not quite clear. And let me finish with a summary and with an outlook. So what was useful? This quaternionic description, the theorem of Kamberov-Pedit-Pinkall relating isothermic surfaces and Bonnet pairs, integrable discretization, structure preserving discretization, because it helped us to find out what are the important properties. And then the smooth construction was quite involved, but it was based on classical results of Darboux. And the outlook, what kind of problems are interesting, what is not clear is, do they exist embedded Bonnet pairs? You have seen that there are sort of a lot of self-intersections. And are there planar curvature lines required? Maybe there are Bonnet tori without planar curvature lines. So here you see it's a solution of a classical problem in differential geometry, and it uses ideas from discrete differential geometry, which I think is quite remarkable. Okay, so thank you. I will finish here.
Thank you very much. Thank you. It's amazing. I mean, it's sensational results. So it's very, very interesting. Are there any questions?
Thank you.
Well, I'll just start. I wanted to ask you about these periodicity conditions. They probably form kind of, well, there are two periods on the torus, right? Two cycles. And are they linear? I mean, well, they're probably non-linear in epsilon, but they're linear in as homomorphism on H1. Is it right? On the
So
first
these periodicity conditions are quite different. Yeah. So we have planar curvature lines, and therefore it's quite easy to control the periodicity along these planar curvature lines. You look, you have planar curvature line, which is closed. That's just a formula. You can control this explicitly. And then you can control also rather easily what is going on your Bonnet pair. So it's a simple periodicity condition. What is much more difficult to investigate is the periodicity condition in the second direction, where you don't have this planar curvature line, and then you should really develop all this machinery. For examples which we are considering, it's quite involved. Yeah. So second elliptic curve appears, and I really didn't have time to explain all the details. So there is an intermediate step with this example with spherical curvature lines. So because it can be investigated analytically. So we have one family of planar curvature lines and the second family of spherical curvature lines. It turns out that all these, the centers of all these spheres lie on one axis, and therefore finally this second periodicity condition is reduced to one-dimensional periodicity condition along this axis. Yeah, so this translation vector which you have is oriented along this axis, and then it allows us to formulate it analytically and to solve it analytically in the case of spherical curvature lines in the smooth case. And finally, the final step to generate more general surfaces, just a perturbation theory. Yeah, so implicit function theory.
Very interesting. Thank you. Any okay, I have one more question because there are no other people wanted to ask. I just wanted to ask you about higher genus, let's say genus 2. Do you think your method may be extended to genus 2 surfaces?
It's difficult to say. Yeah, so we have a good experience of working with surfaces of curvature of constant mean curvature. So, and this is a problem which I would say with the same nature but simpler. And the problem about constant mean curvature tori, it was solved in the 90s, 1990. And after that, it took maybe 20 years before the problem of higher genus was treated analytically and results were obtained. So I think it's doable, but it's much more involved. And now we have just the first step. Yeah. So now we are in the situation, if I may compare it with the case of constant mean curvature tori, that's the case when Vente has found his tori with constant mean curvature, and then it was a beginning of a big theory. So here I expect that much more can be done with investigation of Bonnet pairs, but the problem of higher genus will be much more involved.
Thank you. Thanks very much. If there are no more questions, I just want to thank Alexander Bobenko and congratulate him with this beautiful result.